Alright, so today's topic in planet Earth, we're looking at topic 4, which is the moving crust. So we'll start off by talking about Earth's structure and the layers of the Earth. So at the very top here, which is labeled A, that is the crust. So that includes the layer that we walk on. It consists of the home to plants, animals. It consists of soil. There's also some deeper areas where minerals get mined and oil and gas are formed. It's very thin under parts of oceans. In some places, it'll extend only about 5 kilometers deep, but in other parts, the continents, it can reach a depth of 60 kilometers. All right, so that is the crust, about 5 to 60 kilometers. Next, we have the mantle. The mantle is divided into two parts, the upper mantle and the lower mantle. So it's right under the crust. It's made of a rock material. The upper mantle is solid, and together with the crust, it's called the lithosphere. The lower mantle here, it's partly melted. It kind of has a consistency of taffy. So the rock material in the mantle, it can flow very slowly. Next we have this area here. This is called the outer core. Also note the temperatures. Temperatures are getting increasingly hotter as we go deeper into the earth. So outer core, this core here, it's composed of iron and nickel. The temperature is over 5,500 degrees Celsius, very, very hot. And the nickel and iron here are found in liquid form. And lastly, we have the inner core, which is a solid ball. So because of the intense pressure of all the layers, it forces this inner core to become a solid ball. And inner core has a temperature of over 6,000 degrees Celsius. All right, so we can see in this diagram that each layer of Earth is cooler than the layer below. Okay, I'm going to pause here. Okay, so those videos kind of spoke a little bit about how there is plate tectonics and they're moving. So what is the evidence for continental drift? So firstly, if you look at this map here, we have this bulge of South America, and it looks like it can fit into this indented side of Africa. So continents looked as though they had once been joined. So Alfred Wegener, he's a scientist. He noticed that the outlines of continents looked as if they could fit together. So here is a diagram of what it may have looked like. This is called Pangaea. It's the supercontinent, meaning all lands. So notice how they were all connected together, kind of like puzzle pieces. What other evidence? There was biological evidence as well. So Wegener noticed that several fossils of similar plants and animals have been found on different continents. So for example, like fossils of these organisms here, and these ones and these ones. So, Mesosaurus lived in freshwater lakes, and its fossils have been found in eastern South America and southern Africa. Listosaurus could not swim at all, but was able to travel from South America to Africa. Okay, this is a map showing some other fossils as well. This is from the textbooks if you want to take a look at that. So again, fossils that we can see in South America were also being found in Africa as well. So what is continental drift? This was a theory about Earth's structure, that the continents have slowly changed their position over time. So it's the slow movement of continents. So Wagner, he studied the fossil evidence and the interlocking shapes of the continents, and he concluded that the continents must have been joined together when the fossil animals and those plant animals had been alive. And over thousands, maybe millions of years, the continents gradually moved to their present locations. And Wagner called this explanation continental drift. More evidence. There's evidence from rocks. Wagner discovered that geologists had found similarities in rocks on both sides of the Atlantic Ocean. There's a mountain range called the Appalachians. It's in eastern North America. It was made of the same kind and ages of rock as the mountain range that ran through Britain and Norway. Fossils that have been found of trilobites have been found high up on the Himalayan mountains in India. These trilobites, they roamed ancient seas 250 to 500 million years ago. So evidence suggests that India was once a separate piece of land, and many millions of years ago, India drifted into Eurasia. The collision that pushed rocks containing fossils from the bottom of the sea, they pushed them up to the mountain of the Himalayan mountains, up to the top of the Himalayan mountains. There's also geological evidence of climate. There's coal beds that exist in North America, Europe, and Antarctica. They're now in moderate to cold climates, but coal is formed from rich, luxurious plant life in a tropical, swampy environment. So how did tropical plants grow there? Was the climate different? Ancient glacial deposits, 200 to 300 million years old, were found spread over the southern hemisphere. So layers of deposits left behind by glaciers were found in southern Africa, South America, India, and Australia. And under the deposits in some places, there were grooves in the bedrock showing the direction in which the glaciers had moved. And all of these locations now had very warm climates, much too warm for glaciers. The response to Wagner wasn't a positive response. He could not satisfactorily explain the origin of the force that was moving the continents. So therefore, the scientific community back then rejected his ideas on continental drift. Okay, I'm going to pause here. We'll watch this video. All right, so we're looking at plate tectonics and the moving crust. So firstly, we're going to talk about sonar. Sonar stands for sound, navigation, and ranging. So it's a technology that bounces sound waves off of an object to determine its distance from the source of the waves. So from the sonar, we've been able to see that there are mountains on the seafloor. There's long mountain ranges or ridges in some places, just like we see mountain ranges that existed on land. There's something called the Mid-Atlantic Ridge that we saw in a previous video. It's a mountain ridge that stretches from north to south along the middle of the Atlantic Ocean. And the features that were found on the seafloor are very similar to the features that are found on land. So this is just showing how sound waves can be used. And this is a map here showing the mid-ocean ridges and trenches and so on. So there's this theory of seafloor spreading. It's the process in which an ocean floor slowly increases in size over time because of the formation of new igneous rock along a fault. And there are these instruments here, magnetometers, that can detect the direction and strength of a magnetic field. The magma that forms igneous rock, it contains iron-bearing minerals such as magnetite, and these minerals, they line themselves up with Earth's magnetic field. And as the molten rock hardens at Earth's surface, those mineral particles, they stay in line with the magnetic field. So those the magnetic reversal stripes, they must have formed at a different time, a time when Earth experienced a reversal of its magnetic field. If the stripes lined up with the ridges, it could mean that the seafloor was spreading. It also meant that new rock was being formed at the mid-ocean ridges. All right, and that has led to scientists and their theory of seafloor spreading. Deep sea drilling, tests of rock samples have shown that younger rock is closer to the mid-Atlantic ridge and older rock was closer to the continents. Scientists found that the Atlantic Ocean is getting wider by about 2 centimeters every year, which is confirming the theory of seafloor spreading. Okay, so here the plate movement deep underwater. New crust is continuously forming from the lava at the mid-ocean ridges. Okay, gonna pause here. Okay, so the theory of plate tectonics is that the crust is moving. Earth's crust is broken up into pieces, which are called plates. Those plates are always moving on Earth's mantle. When two plates are pushing together, they're called converging plates. And when two plates are pulling apart, they are called diverging plates. Here we see convection currents. It shows one way that convection currents might move plates. So it's one reason, it's one explanation, is that convection currents in the mantle under Earth's crust, they move the plate. So convection current is this flow. It's resulting from the rise of warmer materials and the sinking of cooler materials. So here, looking at convergent or collision boundaries, a diverging boundary is one where two of Earth's plates are moving apart. So the mid-Atlantic ridge on the floor of the Atlantic Ocean, that would be an example of a diverging plate boundary. Okay, so moving away, and at this type of boundary, we have lava that flows from the ridge to form new oceanic crust. At converging boundaries, plates are moving towards each other. We can feel like earthquakes. We can see mountains, volcanoes. Those all grow up at or near those boundaries. A subduction zone is an area, it's a place on Earth's crust where high pressure, it pushes one very large piece of rock below another. And usually when we see earthquakes, they're often formed in those subduction zones. All right, so kind of seen right here. And then I have a video here on plate tectonics. This is the brain pop one. I'm just going to pause here.